All right, so now we move on to lesson 23, which is conservation of energy. This goes hand in hand with lesson 22, which in lesson 22, we introduced the idea of what are the energy forms that we're going to be dealing with. And primarily, we established that we're going to be dealing with mechanical energy and that all the other energy forms we're going to save for physics 30 when we get more into atomic physics and that sort of realm. But at a more macro level, we're just going to deal with the conservation of energy that deals with mechanical energy, namely we're going to have some sort of potential, whether that be some sort of gravitational potential or spring potential or elastic potential. And then we're going to deal with kinetic energy, which is the motional energy. Now, in conservation of energy, the law of conservation of energy simply says that the amount of total energy in a given system remains constant and that energy can be transformed from one form to another, either kinetic or potential, or from kinetic to heat, but the total amount of energy is conserved. And thus we get this statement that the initial energy equals the total final energy. Now, the way we're going to write this in class and throughout the examples is I'm going to always write it as the sum of the initial energy or sum of EI is equal to the sigma or sum of the energy of the final. And we're going to write that a lot to start our problems just because we want, when we say total, we're summing up or we're taking the sum of all the given energy. Now, to solve, we're going to use the basic method, which is a four-step method that involves how we can set these things up to be successful in terms of how can we identify the energies, how can we organize them, and then how can we make the proper substitutions. So first and foremost, anytime we're dealing with conservation of energy problems, our first problem is going to be dealing with, well, we got to figure out what are the different energies at the beginning, or what we can denote or designate as our initial energy, or EI. So we're going to figure out, is it kinetic energy? Is it gravitational potential? Is it a mixture of both of them? We want to figure out exactly what's happening at the beginning. Once we establish what's happening at the beginning, we're then going to shift our idea to figuring out what the end energies are. So is it kinetic potential? Is it a mixture at the end? We're going to figure that out, and we're going to designate that as our EF, or final energy. We're then going to say by conservation of energy, it gives us the following, that we can say that the initial energy equals the total energy in the end, or the final energy. And then lastly, we're going to make some substitutions from our formula sheet and solve for the requested value, whether that be speed, whether it be height. They could ask a bunch of different things. They could say, what is the spring constant, K value? And we've seen that in the previous lesson, but we're going to get even more specific with it here. Okay, now, in our first situation of conservation of energy, we're going to deal with isolated systems. Now, simply put, isolated systems mean that the total mechanical energy is conserved and that there is no energy loss due to friction or heat. So we're not seeing any sort of like air resistance or rub against a track or some sort of heat produced from these situations. Most of the time, we're going to get this potential and kinetic energy forms that one transfers directly to the other, or a combination of the energies transfer directly to the other one without this loss of heat or energy. Now, or without this loss of friction or heat or even sound or whatever it might be, and isolated, we just maintain this. Now, in our first example, let's just take a close look at what this means using our method, or our four-step method, and the idea of conservation of energy in an isolated system. A 50 kilogram object falls 490.5 meters. What is the speed of the object just before impact with the ground? Now, here's what we want to look at here. First and foremost, when they say we have an object that falls this amount, what we're going to assume is that if it's just falling and it's in free fall, this initial energy is actually equal to the potential energy. So we have some sort of potential representative of the object suspended in the air. They then say, what is the speed of the object just before impact with the ground? As soon as you see just before impact, what this means is that we have only kinetic right at the end. So our EF is actually the kinetic energy in this situation. We have basically no height because it's like quite literally like the smallest fractional value right above the ground. And it's just before impact with the ground. We want to measure like how fast was this thing right before it came to the ground. And another way of saying this would be like before it came to like the impact or rest position, because we want to determine what was that total energy transfer from potential to kinetic. Now, just to draw this out roughly visually, what I'm going to do is I'm just going to create a bit of a ledge here, and then I'm going to have the object that's being suspended. So I'm going to draw like maybe a box like this, and then this box is going to fall some amount of distance towards the ground, and then I'm going to mark this piece here right here as 0 meters, or that this is the ground. Now, in this problem, visually, we have that our initial energy is the potential, our final energy is the kinetic, but we know that if I go from potential energy to kinetic by conservation of energy in an isolated system, these two energies will be equal to one another. So if I know what the energy at the top is, I know what the energy is at the very bottom. Now, it's in different forms, but energy is conserved in this isolated situation. Now, using our four-step problem, we would initialize what is our initial energy, what is our final energy, which in this case we've established. Our initial energy is the potential of the object being held in the air. Our kinetic is right before it hits the ground, so we've established that. When we move to step number 2, it's going to be now algebraically placing these things in here and starting to solve for the variable. We then find the variable, which is here, and we isolate for the variable. Lastly, we plug in and we solve for the variable, which gives us the following, that the speed of this object just before it hits the ground is 98.1. And so what I want you to notice first and foremost in these problems as well is that if we're talking about isolated situations that involve conservation of energy, a lot of the times the mass that's within the energy is going to cancel, or it's a common factor between the two sides, the left to the right. And so oftentimes our equations are going to eliminate that mass. There will be a situation where we don't eliminate the mass, and we'll get to that very shortly. Okay, now, similarly, in the next problem, they could ask us things like, if I'm considering a snowmobile driving with this much mass and it's traveling at a certain speed, well, as soon as you know it's traveling at a certain speed, you can say that the initial energy, or that EI, is equal to the kinetic energy, but then it slams into a snowdrift. Slamming into a snowdrift means that all of the energy is being depleted, or all that kinetic energy is being basically eliminated from this situation, in the sense of there must be some sort of work that's done to stop this object here. And so we would consider this that work is done, and we need to figure out what that work is that's causing this object to lose its energy in the kinetic form and be stopped into the snowdrift. Now, first and foremost, you'd want to figure out what the kinetic energy is. So we can take that kinetic energy off our formula is the following. EK equals 1 half mv squared. Well, they gave us the conditions of 100 kilograms is the mass, 50 meters per second is the speed. We plug those both in and we get 125 kilojoules. Now, this means that 125 kilojoules of energy must be basically halted, or must be transferred from one form to another by some sort of work. And the work we deem this as is, we say, work done in this situation, or the change in energy, because whenever they say this idea of work being done in the situation, it's really key to implement that the change in energy is equal to that work that they're talking about. So as soon as they say the idea of work, we're changing this kinetic energy into a form that is not mobile, but then is now, we're now into the snowdrift. We've lost that kinetic energy. The work done was that situation of that change in energy. Now, when we look at this, we now have our idea that the work is that change in energy. So this is the same as saying the change in energy, which is equal to the work. And then when we go down below on our formula sheet, we actually know that the work is equal to force times the delta D. And so in order to get force, they say what force of that is applied when we slam into this snowdrift causes us to come to a rest. Well, we come to rest over this 0.5, or they sink 0.5 meters into the snowdrift, meaning that the work must be done over that distance. What force happens? We divide both sides by delta D. And this ends up giving us that the force required is equal to work divided by the change in distance. Or another way of thinking about this is the force is equal to the amount of energy, or that change in energy, divided by the distance in which that change in energy happened. That represents the force. So this is the force the snowdrift would apply against the snowmobile in order to cause it to come to rest. All right. Now that introduces work, which is a little bit more of a non-isolated problem than anything. So we're still having this energy go from one form to the next, but we really want to look at this and be like, we're going to focus on this type of example for the first bit here, where we talk about these isolated situations. Okay, now on the next page, we're going to look at another example here where we have different forms of energy that are happening. And remember, we don't just have to go in Science 10, a lot of the times we went from the mechanical energy, which is equal to that EK and EP happening at any given point, they often directly transfer to each other. Well, in the situation of example 3, we have some sort of 5 kilogram object which is thrown vertically down from the top of a 50-meter tower with a speed of 15.0. What is the speed of the object at the bottom of the tower just before it hits the ground? So again, this one is extremely similar to the one we saw before. I'm just going to draw out a situation here. So here's our height. The tower, I'm just going to draw it down like this. I'm going to write in that this is 50 meters here. Now, the object, instead of just being dropped like it was in the previous one, now it's thrown down. And I'm even going to use a little bit of a neater marker there to represent this throw. We have some sort of initial velocity, which is equal to 15 meters per second on the way down. And then they want us to determine the energy at the bottom, or what is the speed at the bottom, which comes from the energy at the bottom. Let's just label a couple things. At this very top piece, we have some sort of potential, and we also have some sort of kinetic, and I'm going to call it kinetic initial. So I'm just going to erase this just to make it a touch neater here. So if I erase this and bring it back, because I want to make sure everything fits here, this is going to be potential energy up here, plus we're going to call it the kinetic I, or EKI. Now, from here, we're then going to label the energy at the bottom, because that's our other responsibility. What's the initial energy? What's the final? At the very end, we have EKF. This is the final position right before it hits the ground. If you really wanted to, you could even draw in that right at the bottom of the tower. This is representative of a height which is equal to 0 meters right here. That means just before it hits the ground, it has no potential but all kinetic. Now, from our equation here, again, we're always establishing what is the total energy, what is total energy in the beginning, total energy in the end. We then established it was EPI, EKI is equal to EKF. We bring out their formulas in terms of we can distribute or actually go to our formula sheet, and from our formula sheet, we can actually plug these in, or the equations for each of these energies. So I'm just going to write in that these come from the formula sheet. You do not need to memorize these. Now, they do a little bit of algebra with this equation in terms of getting it to VF isolated and then canceling the M's. But what you could do to simplify your job is if you realize M is a common factor right as soon as you make that substitution, I would just cancel it there. It's probably going to save you a lot of time. Rather than having to cancel it down here once you've done all this algebra, you may as well just cancel it while you see it as a common factor across the linear equation, or across the equation once you make that substitution. And then when you're moving variables across the equal sign, it just is a little more intuitive. You do a little bit of work with this, and you end up getting that the final velocity right at the bottom is 34.7. And to nobody's surprise, if you throw an object down and it experiences some sort of free fall, that change in energy is going to have this object accelerate down. And although it's changing energy forms in terms of it had potential, now it's all kinetic, essentially the way you can think about these problems is if you had a mixture of both of them up at this height here, where it was going 15 meters per second, at the very bottom, when it all becomes EK, it's like you took all of this EP and gave it to the EKI. You would expect to see a larger EKF, which means a larger speed at the bottom than the top. So this should be of no surprise to us. Okay, now I'm going to skip forward to dealing with pendulums in an isolated system, or pendulums as an isolated system, and then we're going to talk about springs as an isolated system. Now, in the next unit, or in our simple harmonic motion unit, we're going to go into these things in a ton of depth. But for now, when we talk about energetics and we're talking about these being within isolated systems of conservation of energy, what we're going to do is we're just going to break them down in a way that we would have done very similarly in Science 10, just with a little more detail. So first and foremost, let's go off to the side here. What we want to do is we want to label all the very critical pieces, including equilibrium point, where energies are minimized and maximized, where velocity is minimized to maximum, whereas height is minimum and maximums. We want to include all this really good detail. What I would do right away, and we did this in class, create a line down the middle. And what I want you to do down this middle here is label a couple things. This is what we call the equilibrium position. So it's going to be important to make sure you have this noted in here. Equilibrium position. There we go. Now, if this is the equilibrium position, there's a couple things that happen here. The kinetic energy is maximized. And so I'm just going to make sure I put this here. EK is maxed, which I know it says it in the sentence below, but we just want to make sure we label it for ourselves. EK is maximized. And at this position, this is where we also see the speed is the greatest. So this is where we see the greatest V value, or greatest speed. There we go. Now, off to the sides, we see the highest point here. Oh, and I should make sure I note this too as well, because we don't want to overlook this piece. On the very bottom here, I would recommend you just put a dotted line, and you would represent that this is a height of 0 meters, or this is the bottom position. This is the lowest it would go. Now, it's not always true that this would be suspended or not suspended above the ground, so meaning it won't always have a height of 0, but technically what we could always do is make that reference point 0, and that would really help our job here. Now, if we do this, This is nice because now we've completed all the pieces that are talking about that equilibrium position. So this is where it would be at its rest. And that might even be another note you want to make here is this is the rest position. So if I was to apply no energy to the system, the pendulum would sit exactly at that equilibrium point position or this rest position. Now, if this thing is swinging backwards and forwards, we know the EK is maximized here at the equilibrium position. It also has the greatest speed, but we also want to look at this and be like, okay, what's happening at the endpoints? At the highest points, we have a potential energy which is maximized. To nobody's surprise, if it's at its highest point, that means it has the most height. We maximize our potential energy. From here, we can actually say that our speed is minimized, or more importantly, our speed is actually 0 meters per second. Because when we look at this, our EP maximum is that max height. When it gets to these positions, it pauses and then goes back the other way. And so if it pauses and goes back the other way, our speed is 0, which should make sense, right? Because if you have your EP maximum, you have no EK or no motion energy. Now, the other piece we want to write in here is the following. I want you to draw a dotted line across the top here at this highest point. And I'm going to make sure I do that in black here. There's intentionally a reason why here. So I'm going to draw a dotted line right across the top. When we look at the difference between here to here, this is that change in height or the change from the highest point to the lowest point. And so from its highest point in the swing to its lowest point, we consider this the overall height in which the highest point would reach. All right, from here, there's one more annotation I want you to make, and it's the following. I want you to put an arrow to the middle section here and an arrow to the middle section here. In these middle points, the total mechanical energy, or the EM, is equal to a combination of the kinetic energy plus the potential energy. And so neither one is maximized. Anytime you're in these middle sections, which I could even highlight by green here, if I'm in the middle here, anywhere where these arrows are, as it rocks back and forwards here, we're going to consider it a mix of kinetic and potential. So they'll be very specific in the problem. They'll say, given certain information, it will be very obvious if they're in the middle or if they're at an endpoint, meaning they've maximized the potential or kinetic or whatever it might be. Now, when we look over here, what you might want to do is consider the following diagram, and I would definitely write this in your notes just so that we can see what's actually happening in this pendulum situation or even the spring situation for that matter, because this diagram will apply to both pendulums and springs. So realistically, you could even write this in here that this applies to springs as well. Okay, now, and I'll put a slash there just to make sure it's obvious. Okay, first and foremost, in the diagram, you want to draw a horizontal line across the top. We're going to consider this to be our total mechanical energy at any given point. We know the total mechanical energy in an isolated system is conserved. Now, I'm going to draw two lines here. First and foremost, what if I consider the potential energy at any given point in this pendulum? As I'm on my left-hand side, we know it's maximized. As it approaches the middle, it becomes minimized or 0, and as it goes back out to the right-hand side, it becomes maximized. And so we're going to consider the red line our potential energy. In the opposite situation, if I start on the left, I have no kinetic but all potential, and so this is going to be 0. It's going to reach its lowest point in the pendulum, which is its actual maximum EK, and then this is going to collapse back down to the following. And we're going to call this our kinetic energy. One thing I want you to notice about this graph is the following. If I took the sum of any 2 points, and I'm going to use my laser pointer here, if I take the sum of the points of the red line and the green line at any key interval, what we would see is that this plus this add up to make the mechanical energy at any point. So lowest point, which is 0, plus here, well, the total between these two is the mechanical energy. If I take the sum of these two, they would add up to make the overall total mechanical energy. So it doesn't matter where we are, anytime you add up the potential and the kinetic, it will always equal to the total mechanical energy, or sometimes just denoted as E total. I like to write it as EM representing the mechanical, but you might see it the other way. Okay, now, just like the note says below here, you may want to highlight this because it basically puts it down in words for us so that you can have that as a note to keep. Anytime we're in the system, we can always add the two together. Now, a couple of key notes or a couple of differentiating points. At the top of the swing, just as we were saying, there's a maximum amount of potential but no kinetic. Therefore, we can say that the total energy at that point is EP max or only potential. And that refers to right here. We then can consider the following. What if instead we're at the bottom of the swing? Well, the bottom of the swing, or the equilibrium position, which is extremely critical to hold on to, which is here, it has all of the potential energy but no kinetic, or sorry, vice versa. It has all of the potential which has been converted into kinetic. I'm trying to read the point and then also make my own points about it. That can get confusing there. Now, so there's a maximum amount of kinetic energy because we have all motion and no height or no sort of stored energy. Therefore, at that bottom position, we say it's EK max, which is exactly here. And this is also where our speed is maximized. All right, let's consider springs. Springs are very, very similar. They just look a little bit different overall. So let's consider the horizontal spring to the right. Now, this is a frictionless horizontal spring that oscillates backwards and forwards. What does this mean? It goes back and forwards. So if you need to, I would make sure you put this in your notes of, okay, what does it mean to oscillate? It means it moves backwards and forwards across this horizontal surface. Now, if it's frictionless, that means that this is an isolated system. So I'm hoping that if you see these words moving forward, frictionless horizontal surface, this means that the surface is, or the system is isolated. And therefore, there's no sort of heat loss or frictional energy loss or sound loss or air resistance. We're going to take that all out of here. Now, let's break apart this diagram here so that we can make sure we have a firm understanding of what's happening. So when they say equilibrium position, just like when we dealt with the pendulum, it's going to go right down the middle. And what we're going to say is that this is where our kinetic energy is maximized. So we're going to call it EK max. This is also considered to be the rest position. So rather than even the equilibrium position, we can say that this is going to be the rest position where the spring would naturally rest. Now, what we're going to do is we're going to label two other points. I'm going to label what would happen if the object was fully compressed, or the spring with the mass on it was fully compressed to the left-hand side. We would say that if you fully compress a spring, you maximize the potential energy to do work. On the end point, let's say we stretch out the mass fully on this side. What we're going to find is that we maximize the potential energy because there is this maximum potential for, if a spring is fully stretched out, for it to want to bring itself back in towards the equilibrium position. And then often what we're going to do is we're going to denote this change in x as the length of the spring from the equilibrium to its positional point. And so in between here and here, I would make sure you just put a delta x or a change in x. Change in x is always how far are you moving away from the equilibrium position in order to get to the position in which the object, or in this case, the mass attached to the spring, is currently sitting. Okay, now if we look at this piece here, as the spring oscillates backwards and forwards, or moves back and forwards simply, the mass has no potential energy, only kinetic when the spring is moving through the equilibrium position. That's a very, very critical piece here. So all EK in the middle piece and no EP. The mass only has potential energy when it's at its endpoints, when it's at its maximum displacements. That X, if you really wanted to, you could classify it as the displacement from the equilibrium. And then at any other point in this oscillation, just like we dealt with the pendulums on the previous example, what I want you to do is just put an arrow in between here and an arrow in between here. Anytime we're in the middle section, or when we're just past the equilibrium but not quite at the endpoints to the left and the right, it means that the mechanical energy can be summarized by some sort of EK plus EP. It's a mixture of potential and kinetic because there's a little bit of that compression or a little bit of that stretch that wants to cause the object to have some sort of stored potential, but there's also some sort of motion going on in these middle points or in these kind of like more intermediate median points. Okay. Now, when we look at these, just like we dealt with before, just like we looked at with the pendulums, assuming it's isolated, at any point we can just add the two together. And so again, we could break it apart into a left position, right position, median position, right at the middle, or the equilibrium position. There's lots of spots to look at, but we always want to say that the total mechanical energy is conserved in these isolated situations. All right, now, what if we go on to conservation of energy, but in this case, non-isolated systems? Well, non-isolated systems, unlike the isolated systems, is now we can lose energy to either heat, sound, friction, whatever else it may be that is affecting this and causing work to be done in this situation. The total amount of energy still is conserved. So we still see that the overall energy is conserved, but some of the mechanical energy is now converted to these external sources, which we're going to call work. Now, consider the following example. If I have a 5-gram bullet and it's entering a block at 350 meters per second, so it's shot from a gun and it has this initial kinetic energy, we want to just indicate that right here, that the original energy we have is this kinetic energy. And so I'll even call it EKI, which is equal to the EM, which in this case is the mechanical energy for this situation. But I'm going to classify this even more specifically. This is just generally the EI. Now, it goes into a block which is 20 centimeters wide, and then it leaves the block with this speed here. So we now have this new EK, or the EK final, which is equal to the energy in the end, or our final energy. Now, just like we did with the isolated systems, we're doing the exact same problem solving type, but now we're going to introduce this idea of work being done to affect or change the energy in this situation. So they say, as soon as you see this here in the problems, what was the force applied to the block, or force applied to the bullet by the block? I want you thinking what work was done. And I'll make that note here. There we go, question mark. And then this is another way of saying work, or what change in energy was done in this situation, because that will help us find the overall amount of force that was applied by the block, or applied to the bullet by the block, just to follow the wording of this problem. Now, just like we did before, let's label our initial and final energies. Now that we understand what they are, we had some sort of EKI, some sort of EKF. We then establish that in its formula, but what we're going to do is say, if we had a total amount of mechanical energy in the original piece, which was the kinetic, and we transferred some of that kinetic energy, but not all of it, we want to now introduce this idea that work was done by the block on the bullet. Now, from there, what we can do is we can do our substitutions off the formula sheet. We realize that force of friction is that frictional, or is that force that's causing this object to be slowed, because friction works against the overall directionality or the original direction of the movement of an object. And so we're going to make the substitutions of, we know EKs are both 1/2 mv squared. And what they do is they put the subscripts here, which I really like. So I would make sure you subscript your V's and subscript your H's when you're solving these problems. When you plug in for the work here, we know work goes on the right-hand side of the equation because it was part of the product or the end energy. You can phrase it this way: this work that's done by the block is also equal to that change in the kinetic energy. So if we have this change in the kinetic energy off our formula sheet, we know that W is equal to F delta D. And in a horizontal problem, we don't have to involve cos theta, so just F delta D. We now take this equation, we isolate it for that force. Once we have that force, we then can just easily figure out the resistance. Now, what you could have done in this problem is you could have just said, hey, let's solve for that work here, just isolate for W block, and then go to this equation here as a two-part problem. But they just make that substitution within the problem and then just solve for F within the whole thing. And we end up finding that the force of friction causing this slowing of the bullet is 1,250 newtons. Now, this should be of no surprise because the block is quite thin and the bullet speed drops by quite a significant margin. It's about 200 meters per second. So if this thing drops by that big of a margin, we're going to have a lot of frictional force that acts against this bullet as it enters the block. Okay, so anything that involves work will have a very similar situation to this, where we're going to have to account for some sort of overall work that's being done or an overall change in energy that's affecting this situation. Okay, now I just want to take a look at one more problem here that involves some sort of energy loss or in a non-isolated system, and it's the following. What if we have an object that's sliding down an inclined plane and we have 25 kilograms of an object resting at the top of this 15-meter high inclined plane, and it begins to slide down? At the bottom of the plane, the object has this speed. So right away, here's what I want you to do. If they say that the object is at the top and ready to begin to slide down here, what we're going to do is we're going to say that this is going to be potential energy. And more importantly, your initial energy, or your EI, is equal to the EP. Now, as this thing begins to slide down and then eventually reaches the bottom with a speed of 14, we're going to see this as the final energy, or this is going to be our EF, which is equal to EK. Okay, what we need to now account for is, they say in the problem in part A, how much heat energy was produced, or what was the change in energy, or that overall change in mechanical energy that was a result of this object losing some sort of energy to heat. And so initial energy equals final energy. We set this up, or what we're going to do in our problems when we get there, our practice problems, is the sum of the original energy equals the sum of the final energy, or the EF. What they do is they go EP, which is that total original energy, it was unaffected, is equal to the kinetic energy at the very bottom, but we now need to add in this heat energy, or this change in energy, change in mechanical energy, if you want to put it this way. I'm going to rephrase it to this. The work done is equal to the change in mechanical energy, or that EM, as we transfer from EP to EK, which is then also equal to this EM, or what we're going to call, or sorry, EH, I should say, which is the heat energy. There we go. So we have to add in for this idea that work was done and that there was the heat energy. Now, it's as simple as taking this formula and just isolating it for EH. When we isolate it for EH, we're going to find that there was a pretty significant amount of joules that were lost to heat. So 1.23 kilojoules, that's the same as 1,230 joules. So I'll rewrite this and say it is 1,230 joules of energy lost to heat, which is a significant amount. Now, if they end up saying, what is the frictional force? Again, what we're going to do is we're going to look at this from a work standpoint and be like, if we want the frictional force over a certain distance, even from science 10, we always know that work, or that change in energy, or in our case, the change in that heat energy in this problem, is going to be equal to the work. And therefore, this is also equal to force delta D. Now, if this is a frictional force, we're just going to get more specific and say that our heat loss is equal to the frictional force over some distance. And when we do this, we can isolate this by dividing away the distance, or dividing away delta D. And so the change in heat energy, or that work done in the system, is equal to, or the work done in the system in terms of heat energy, divided by the distance in which that energy change happens, gives us that frictional force, which then leads us to this. Now, if we look at this in the grand scheme of things, this isn't a ton of frictional force. It's a decent amount for sure, 35.1. It's nothing to be like, that's not a lot. But when we look at it, it's a decent magnitude, nothing extreme. It's definitely not in the hundreds or even thousands like it would be for, like, if we're talking about like forces of centripetal force, or all these forces we've talked about through dynamics. Sometimes these forces were very large. And this is a, decent force, but relatively, because we don't have anything to directly compare it next to, we say, it's a relatively high frictional force, or, kind of right in the middle. We don't know for certain. More importantly, we just want to make sure that all our information along the way is proper, and that the one major thing is, and I'm going to point this out right here, in the solution above, they gave us kilojoules. What we want to do is always answer things, or always use joules in our solutions. So don't be surprised when they take the joules from the previous section and then use them here. So clearly the unrounded version before they went to kilojoules was the 1,228.75 joules. They just rounded it to make it a kilojoule, to make it 3 significant digits, but you'd always want to use the unrounded. All right, now let's try our own problems here. Here we go. This is where we actually get to apply our own knowledge into these things and deal with isolated and non-isolated systems and see how they work. So first and foremost, we have a motorcyclist that's trying to leap across the canyon, and they're shown in this figure driving horizontally off the cliff. When it leaves the cliff, the cycle has a speed of 38 meters per second. Ignoring air resistance, as soon as they say that, we can say that this is isolated. So I'm going to fill that in here. This means isolated, meaning there's no work done due to friction, heat, or air resistance. Find the speed at which the cycle strikes the ground on the other side. Okay, right away, we look at this and it kind of looks like a projectile motion problem, which you might be tempted to solve it like that, but let's not for now. What we can do in this problem is, you can do this a slightly harder way or an easier way. I'm going to do the slightly harder way for this example, but then explain what you can do in the next problem, because the one that follows after this, we're going to do the method, and then you can compare and contrast between these. Originally, we have some sort of height, which is 70 meters, and it goes down to a height of 35 meters. Well, what we want to do is talk about the initial energy. There is not only kinetic energy here because it's moving, but there is also some sort of potential because it is 70 meters off the ground. When it lands, we also see that there's kinetic energy because the object is moving, and there's also potential energy because our height in this case is 0 right at the very bottom here. So we're going to consider this to be where the height is equal to 0 meters. As long as there's height above the ground, we're going to consider this to have some sort of potential energy. Now, I'm going to get even more specific than this in terms of this. I want to write subscripts. This is EKI, EPI. This is EKF. I shouldn't put I. I'm going to erase this just to make sure it's good. This is going to be EKF, or the final kinetic. This is going to be our final potential. Now, let's write this into our equation. Once we've established what these energies are, I'm going to get more specific and say that the sum of the energies in the original position is equal to the sum of the energies in the final position. Now, we're going to expand this out to say the kinetic energy in the initial position plus the potential energy in the initial position is equal to the kinetic in the final plus the potential in the final. Now, off our formula sheet, here's where we go to that section on the bottom left, which deals with all these EKs and EPs. We're going to expand them all out. So it's going to give me 1/2 mass VI squared. And I'm going to use subscripts to be very specific. This is MGHI, which is equal to 1/2 MVF squared plus MGHF. Now, right away, just like I was saying in some of those work through problems, cancel out your masses. If this is a common factor or a greatest common factor between all of them, we know that if I divided by mass, it would go off of all the terms. The other thing I'm going to do is I'm going to actually multiply both sides by the 1/2 because I hate fractions in these. I really don't like seeing fractions, so I'm just going to multiply both sides by 2. And I know this side's a little messy, so maybe I'll just write it below like this. Okay, in our next line, it's going to give us the following. If we distribute the 2 and we've canceled the masses, it's going to give us 2vi squared plus, or not 2vi squared, I need to backpedal that because the 1/2 and the 2 cancel. It's going to be vi squared plus 2ghi, which is equal to vf squared plus 2ghf. Because again, we're going to distribute that 2 on both sides. What they asked us to find is the vf, so I'm going to isolate for the one highlighted in yellow here. How I'm going to do that is I'm going to subtract away the 2ghf from both sides. So 2ghf minus 2ghf. Now I'm going to plug this all in and say that my vf is equal to the square root of, because I want to isolate that vf for an individual vf, it's going to be vi squared plus 2ghi minus 2ghf from the other side there. Now again, you may think if you don't use subscripts, you'll be like, oh, it's 2gh and 2gh and they're positive and negative, so cancel them. No, that's not right, because the h here is different for both of these, hi and hf. It's the importance of using subscripts. Now, let's plug in our information here. Hopefully I have enough room here. I'm going to even drop this just to make sure. The vf is equal to, and I'm going to do a very long square root because we probably have a lot of information here. The first vi comes from the very top. It was 38 meters per second. So 38.0 meters per second squared plus 2 multiplied by 9.81 meters per second squared multiplied by the height, which was in the original position, 70 meters. There we go. And then this is going to be minus, this is going to be, we don't have a lot of room to here. I'm just going to do it below here. This is going to be 2 multiplied by 9.81 meters per second squared multiplied by the new height, which is 35.0 meters. There we go. And if we take the square root of this, we're going to find that the VF is equal to, the nice thing is I'm going to cheat off my answer key here, 46.2, and we end up getting that as the final. So this is 46.2 meters per second. Great. Now, yes, is this a lot of algebra or is this a lot of steps? For sure, definitely. But what I'm going to show you in the next way is how we can almost simplify this. This is a great solution. Like if you did this and you did all of this work, fantastic, excellent. This looks great. But when we look at this overall, I just don't want you to think about this as the only option. There is a way to eliminate some of these energies within this, but also be talking about the exact same thing. And so in the next problem, we're going to do exactly that. Now, one note I'm going to make about this is that please do not use projectile motion with these. Within this unit, we want to be very specific and deal with these in terms of energetic or the change in energy. So I can't emphasize that enough. And the reason is because when we talk about these, in the previous unit or in unit A, we said that this was a Vx. And when we solve for Vf, this is actually equal to the overall velocity at that point. It's not just Vx. So if we start crossing over to projectile motion, we're going to confuse ourselves. So I just recommend you don't. just talk about energies, and then when it comes to projectile motion, if they ask for that type of solution, we can do that, and the setup will be very nice for that. Okay, now here's the situation for number 2. And again, I'm going to explain this in a way that might simplify this for us. In the problem, we have some person that's swinging from a rope, starting at rest on this cliff up here, and they're swinging down on this rope swing, and then letting go right here and dropping into the water down below. Now, what we need to be very clear about is that this is the original h equals 0 down here. So the water is where we're actually looking at the h equals 0, meaning when you release or when you reach your final energy before you leave for the water, this is where it's actually not h is equal to 0. So what we can do is to force this problem to be nice for us and eliminate some of this confusion here. What we're going to do is we're actually going to make this where at the very bottom, right before he releases here, or right before this person releases it, we're just going to make that h equals 0. And this is going to help us simplify this a ton. So h equals 0 meters. Now, what this means is that originally, if they're at rest at the top, we're going to consider this to be all potential energy. This is the potential, you can even consider it the potential energy maximized because it's at its highest point and there's no movement. We then look at the bottom and we're like, well, if that's where h equals 0 and the person releases at this point, we're going to consider this to be the EK, and not only the EK, but the EK maximum because there's no potential energy left. Now, if this is an isolated system, we can make the number one assumption that these two energies are equal to each other and that one form is transformed into the other. Now, one thing I want to note just really quickly is that, again, anywhere in this middle piece where I'm going to designate by green, this could be symbolized by EM, which is equal to EK plus EP. It's the mixture of energies in the middle here. So if you're in anywhere between these two red energies, or the potential max and the kinetic max, it's a mixture of two energies, kinetic and potential, because there's some height and there's some motion. Now, the nice thing is this creates a really nice equation for us, which we have the following. The sum of energies, or the sum of the initial energies, equals the sum of the final energies. Our initial energy is equal to EP max. Our final energy is equal to EK max. I'm going to substitute off my formula sheet, mgh, which is equal to 1/2 mv squared. I'm going to cancel my masses here because if it's a common factor, we can get rid of it. I'm then going to multiply both sides by 2 because I want to solve for my v squared, or solve for the v more particularly. And I'm just going to move this over just to create a little bit of space for us because we'll probably need that right margin there. So I'm just going to make it like this. There we go. This is going to give us the equation that is 2gh is equal to v squared. I'm going to square root both sides in order to get my velocity, or my maximum speed. And this is going to give us v is the square root of 2 times g, which is 9.81 meters per second squared, multiplied by the overall height. In this case, we actually failed to mention this. If the rope length is 6 meters and that 6 meters is maintained along this semi-arch, it means that this change, or this height here that we're going to have here, is equal to 6.00 meters as well. So from the top of the tree where it connects down to the bottom where it's at the lake, or where it's at the point where the person releases, we're going to consider this 6 meters, and that will go into our height calculation. So this is 6.00 meters, and that's all square rooted in brackets. Now, this is going to give us a speed of 10.8 meters per second squared at that bottom position, and this would be the speed. Now, we can also make the assumption that this is the maximum speed. So if you want to include that detail here, because it's at the lowest point and there's no potential but all kinetic at this very instant, we're going to consider this to be the maximum speed. Now, in the solution manual that I've included on D2L, you're going to see a more complicated way in which we continue to make the 0 where the water is. So this is where the height is equal to 0, and we solve it during that way. You will find that you actually end up getting this exact same formula here. So if you do h equals 0 at the very bottom, and you solve it where instead we have some sort of EK plus EP at this point, and we solve it that way, you'll find you'll get the same value. And I'm curious, I really want you to look at it, because you're going to see that when we talk about the algebra around this, whether I'm talking about the EP going from here to here, or the EP going from here to here, we're still doing the same math technically. We're just accounting for this little slice at the bottom, but because this piece, or at this level, also accounts for this piece down here, and this accounts for this piece, the common factor here that we can easily see that's overlapped is this piece here. So we can almost just treat this like it's not here, and we'll still end up getting the same energy at that moment. Now, again, look at that solution on D12, just for your own sake, just to be like, I can treat the H equals 0 at that bottom position. And then I really challenge you to go back and look at this problem and do the same thing. Instead of treating it like 0 was down here, what if we treated 0 like it was here? How would that change our equations? How would that change our energies? You would find you get the same value when you make 0 equal right here. Okay, it's all about creating a universal approach of, can we create an approach that creates a reference point that allows us to simplify our work? That's it. So we can either do it in a longer way, or we can create a reference that allows us to simplify our energetics. Okay, let's move on to number 3. We have some sort of 0.4 kilogram mass that's vibrating, or another way of saying vibrating, if you ever see this, it just means it is moving backwards and forwards. So I'm going to say moves backward / forward. Or, oh, spelling force, forward. There we go. Or it oscillates. That's another way to say that. So moves backwards and forwards, or oscillates, or vibrates. All of these are the same. And it's at the end of a horizontal spring along a frictionless surface. As soon as you see this, you know it's an isolated system. So make sure you make a note about this too. I'm going to say that this is isolated. Okay, now if the spring constant, or the K value, is 55 newtons per meter, this is the stiffness of the spring. Remember, if we talk about this piece, and I don't think I made enough of a note about this piece here, is that when we look at this, I may even go back to this on the previous page. So let's actually take a second to reverse. If we haven't done this yet, or if you haven't done this in your own notes, which there's a chance you haven't, I'm going to go back to the spring section, and I'm just going to put 2 things in here. First and foremost, our potential energy is the following. It's this different form on our formula sheet. It's still EP, but it's 1/2 kx squared. Now, the kx, k is the spring constant, which is, and so I'm going to spell this out, that's our spring constant. And it's measured in newtons per meter. Now, what this means is it's the amount of force per meter that is required in order to either stretch or compress the spring. So we often resort to this and we say it is the stiffness of the spring. If you wanted to write that into your notes, that may be a good idea. How stiff is this given spring? When we talk about the x value is the displacement of the spring, or how far it is away from the equilibrium. And this is always measured in meters. Okay, now that we have this potential energy and we have 1/2 kx squared, we can pull this from our formula sheet. Great. I can't believe I forgot that in here. It's an important detail. We'll make sure it's there. So if you need to, and you haven't had this in your notes yet, make sure you write that in there. Okay, with this knowledge, we're going to go back to our situation here and say our K value is equal to this. Now that we know that that's the stiffness of the spring, or the amount of force required to condense or stretch this spring by a meter, we're going to look at this and say, okay, let's first start off by drawing the visual of what's happening here. So here's my horizontal spring, and they say the maximum displacement or amplitude is 15 centimeters. As soon as they describe the maximum like this, what we want to be thinking is that you can either have it as it's being fully stretched out, or you can write it as it's being fully compressed. And the reason, I'm going to kind of draw it in both ways for us. So first and foremost, we could draw it like this, where the horizontal spring is fully compressed and there's the mass on the end right here. Okay, now I'm going to draw in the equilibrium position, which I'm going to put right here. There we go. So if I look at this piece here, this is going to be our EQ point, as I'm going to call it. This is also where our EK is maximized. So I'll make sure to put that in here. And then when they say this displacement is 15 centimeters, just make sure we make a note off to the side here, where instead of the 15 centimeters, it's going to be 0.15 meters. Very, very important here. Now, when we look at this piece here, the 0.15 meters is going to be symbolic of this here. So it's how far it's been displaced. This is 0.15 meters right here. All right, now, because this is a maximum displacement, something also happens at this critical position here. we're going to draw a vertical line right through the center of the mass here and say that if this is the overall maximum extension, it means that this is also the potential maximum. And so I'm going to write that just below here, that this is equal to our EP maximum. Now, what we could also have is, because this is the X value, this is the displacement of the spring in the left direction, maximum displacement doesn't just occur when it's fully compressed, but it also occurs when it's fully stretched out. So what I'm going to do is try to just say, in the neatest way possible, that this continues on. Let's say the spring just continued this way as following. I'm going to put the mass on the end. And I really want to be neat about it, so I'm just going to try to like continue this diagram in the neatest way here. So let me just put like a dotted line through here just to indicate the spring continuing. So suppose the spring was fully stretched out instead. Well, again, this would be its maximum displacement. So on this endpoint, which I'm going to write in with the blue marker here, whoops, if it lets me, there we go. Perfect. So this is my dotted line. I'm going to write that this is where EP is maximized at that endpoint, or at that very stretch point. Okay, the displacement is again this X value, which is right here. So from point to point, we consider this the X, which is equal to 0.15 meters. There we go. So it's still visible for us. And so whether we consider it when it's compressed or stretched, either way, that's the maximum displacement. So because it has this oscillatory nature, we can look at it both ways. Now, what this means for us is, when we solve for the maximum speed in this as it passes through the equilibrium, we can create our initial energy and final energy. It says as it passes through the equilibrium, meaning if I'm fully compressed like this and then I let go, it's going to pass through the equilibrium at its final position. And then when we go from a fully stretched out position, we could then release it and it would want to go through the equilibrium. We're going to write this as initial and final energy in an equation. So the sum of the energy initial is equal to the sum of the energy final, which means that we have this overall energy potential starting and an energy kinetic in the final position. We're going to expand this because it's our spring. We want it to be kx squared, not mgh. And then in terms of the kinetic, we're going to write this as 1/2 mv squared. Now, this is the first situation where we see that the k value doesn't just simply wipe out, or the m value doesn't wipe out more particularly. We cannot cancel the mass, but what we can do when we involve kinetic and the spring potential is we can actually cancel out these factors of 1/2 out front. So that's something really nice about these, is although the masses don't cancel, at least the 1/2s cancel. Now this is going to leave us with kx squared, which is equal to mass times the velocity or the speed squared. I'm going to divide both sides by mass. And when I divide both sides by mass, I'm going to get that the speed is equal to the square root of kx squared divided by mass, which is equal to the square root of, and now we're going to plug in all our values here. The k value was, I want to make sure I get this right, 55 newtons per meter. The x value was 0.15 meters. And we just got to make sure to square it because it was x squared. And then divided by the mass was equal to, let me make sure I get this one right, 0.4. And this is in kilograms. There we go. Now, to get the final solution here, I'm just going to have to do this right below here. The final speed is equal to, in our calculator, 1.7. And I think we're only doing 2 significant digits. I could be wrong, but I just want to zoom out here. No, it's going to be 3 significant digits. So 1.76, this is meters per second. So it's moving at a decent rate. Nothing extremely quick, but definitely a decent speed here. So we put over our answer here, and there we go. Now, it's really important to distinguish that when you look at springs and pendulums, they actually are done very, very similar. So if you look at how the overall situation is of potential on the left and right, or the left and right maximums, your equilibrium point is right down the middle. It's your EK max. It's your resting position. It's where the maximum speed is. So again, you could consider this as the maximum speed if you really want to write this, because this was the equilibrium speed. It's the maximum speed. There we go, and I'll throw that in brackets. All right, we got one more example to do. It's this one here. One of the fastest coasters is 2,000 kilograms in the world, and it's the Magnum XL 200 at Cedar Point Park in this Sandusky, Ohio. Wow. This ride includes an initial vertical drop of 59.3 meters. Assume that the roller coaster has a speed of nearly 0 as it crests the top of the hill. If this is a frictionless environment or a frictionless track, find the speed of the roller coaster at the bottom. Okay, right away, as soon as you see frictionless, you want to say that this is an isolated system, meaning there is no sort of work done. We have some sort of direct energy transfer from one type to another. Now, I'm going to draw in the overall hill here. So let's say, oh, it changed on me. Let's say it looks like this. Perfect. That will do. They're at the very top, and then they reach the very bottom. We want to discuss the energies at both of these. At the top, they said it's relatively motionless, or there's a speed of nearly 0. So we're going to say that this is potential. At the very bottom, it's EK. And so therefore, this makes our job extremely easy, because if we have some sort of height, which is equal to 59.3 meters, and we know that the energies are one type versus the other, we know that if it's an isolated system, we can write it as the change, or the sum of the initial energies, is equal to the sum of the energies in the final position. We have potential energy in our initial position, kinetic energy in our final. Potential goes back to mgh, because now we're dealing with gravitational potential, 1/2 mv squared. Again, when we're dealing with gravitational potential and kinetic energy, the masses can cancel. We're going to multiply both sides by 2. And this is going to give us that we have 2gh is equal to v squared. Continuing this off on the top side here, we're going to get that v is equal to the square root of 2gh. And then lastly, the velocity, or the maximum speed, is equal to, let's plug in our variables here, it's 2 times 9.81 meters per second squared, multiplied by the height, which was 59.3, and we're going to solve that this is 34.1 meters per second right at the very bottom. So this would be that final maximum velocity right at the bottom of the curve after it's made its descent from the top position. Now, one thing I want you to know is that from our lesson here, we've been doing where 9.81 is positive. And the reason I'm making it positive in all these calculations is because if we talk about height, and the height starting and then going down for each of these objects, this is a negative height. So a negative height and a negative acceleration, these would end up just becoming positive if we were to actually put in magnitudes, or if we were to put in direction with the magnitude. So what I tend to do is I just tend to write them in terms of positive, positive, and then that way we get this positive square root. We're not mixing up negatives and positives, and we're not messing up directionality here. We're just saying, hey, if we're solving using energetics, we know energy is some sort of scalar value as a scalar quantity. And so let's not mess around with positives and negatives. Let's just make the overall situation positive, because we know it'd be positive anyway with a negative acceleration and a negative height. But anyway, we know that in the case of energies are scalar values, so we don't want to mix those up. Okay, part B. The actual speed of the roller coaster at the bottom is 32.2 meters per second. If the length of the track is 125 meters, what is the average frictional force acting on the roller coaster? Okay, we now have frictional force, meaning this is non-isolated. Right away, as soon as you see those key words there, this is non-isolated, because there is some sort of work being done that changes the overall mechanical energy in the system. So here's what we're going to do. We're going to write this as, if we know that there is some work being done, well, the sum of the energy in the initial position equals the sum of the energy in the final position. The original energy is the potential energy. This is unaffected, but in the end, apparently we have kinetic plus some sort of work due to the friction. And so I'm gonna call it like work friction, just to be very specific here. There we go. Now we're going to expand this out. This is going to be mgh is equal to 1/2 mv squared. And then this is going to be plus, if we want to figure out what the frictional force is, what we can actually do here is that we can expand this based on the definition of work. We know work is equal to, work is force times the distance traveled. And so if it's force times the distance traveled, I can write this as the frictional force, delta D. And now what we're trying to solve for is this FF. In order to solve for the FF, quite simply, we can just divide both sides by the delta D. And actually, before we do that, we want to make sure we isolate the FF delta D, because it might create a little chaos here. So I'm going to move this term, the 1/2 mv squared, over to the other side, minus 1/2 mass velocity squared. And I'm going to do that to both sides, mass velocity squared. Continuing this off to the other side here, I may just move this little work note just so that we have it in a slightly different spot. Let me undo that. There we go. Perfect. I just want to get it out of the way so that we can actually use our extra space here, or the limited space we have. This is going to give us mgh minus 1/2 mv squared is equal to force of friction, delta D. I'm going to divide both sides by delta D. And when I divide both sides by delta D, we get that the force of friction is equal to, and I'm just going to start plugging in values here. Our mass of the roller coaster was 2,000. So it's going to be 2,000. Oh, I'm going to need a lot of space here. So what I might do is just really try to see if I can extend this out as much as possible. So force of friction is equal to the mass, which is 2,000, which was given early in the problem, multiplied by the 9.81 meters per second squared, multiplied by the height, which in this case was 59.3. There we go. Minus 1/2 m, which is 2,000 kilograms, multiplied by the speed, which the actual speed was 32.2. So this is 32.2 meters per second squared. And then we divide all of this by the overall change in the distance, which was a 125 meter track. There we go. And I'll make sure that 5 is not connected just so that we're making sure that's clear. There we go. Therefore, the force of friction in this situation is equal to, they put it in scientific notation for the answer, but it's technically 1,000 newtons of force, but the way they write it as 1.01 times 10 to the 3 newtons of force. And again, when we look at this piece here, we're just looking for the magnitude of this piece. We don't actually need like the directionality or any piece like that. I know typically in forces, we want to say, oh, it's opposing the direction. So, I mean, you could say this force of friction or the force applied is up the incline or up the roller coaster because it's opposing that downwards direction of the cart. But if we just write the magnitude in here, that is perfectly fine. And here's the way I want you thinking about this as well. In the end, if you want to solve this for whatever the W is, like you could easily go back to this step here, isolate for W, solve for W, and then put it into this equation of W equals F delta D. That is totally fine to break this up. But if you recognize that you're going to have to just end up taking this W and then placing it into this equation, if you would rather, you can just make that substitution within the energetic statement or within your conservation of energy statement and just solve for that force of friction or solve for that distance right away, depending on what you're given. But some questions might even ask just, what is the work done? So you may just need to solve for the W here. All right, massive lesson, massive, massive, massive. You will want to work on this hand-in assignment / the work assignment as we call it in class. So it's not due, but you want to work on as much of this as possible. This was a very dense lesson. All right, good luck.